let me turn on the tape. All right, so we're officially started here. Do not let me forget to roll. This is my custom. Okay, so try to remind me at some point to pass that out. All right, so next time is the test, right? So no lecture less time next time. And remember that homework on tangent planes. That's the last thing that's on the test. And if you've looked at the sample test, you can see that's the last really thing that's covered there on the test. We started last time talking about extrema, functions of two variables. So that means local or maybe absolute maxima and minima, right? Okay, for functions of two variables, right? So that would be peak points and valley points on these surfaces. But we just started that. So we've got plenty more examples to look at of extrema. But that's not on the test, okay? And then there's kind of you'll see kind of a complicated theorem that, if you can remember the theorem, it simplifies finding extrema, but the theorem is kind of lengthy. We'll see that today. Anyway, so this is the last homework that's on the test. So notice I did post the answers to the sample test. I know of at least two small mistakes on there, though. One of them I discovered when I was making the video review. Okay, so the video review is the link to that is also posted. It's about an hour. So if you go to the Blackboard page under where the sample test is, there's also the link to that video. I caught one of those mistakes on the video, so I'll show you this one. I'll show you that one now. And these are just arithmetic errors. And then Fatin showed me another one that I did not catch on the video. So that's now immortalized on that video. But anyway, I'll show it to you here. It's a small mistake. So it wouldn't be consequential for a test. All right, so that's where we are, right? That's for next time. So be preparing your survival card and looking at the sample test and the answers to the sample test, and then the review if you want to look at that review that I made of some of the problems. Okay. Some of the problems on the sample test. Let me see if I can find that review. So here's what the answer sheet looks like. And if you go down to, so there may be other mistakes as well that I'm not aware of because I didn't check all of my answers. But in this part here, 3D, this is a very simple problem. So you just have a function of two variables. In this case, it happens to be a natural log, right? Of this expression, x squared plus y squared minus 1. And the first part here, this is just a gimme for the test, is just to evaluate that function at the input -1 and 2, right? So I'm just supposed to plug -1 in for x and 2 in for y. And I just messed up the arithmetic. I forgot to subtract the 1, I think, right? This is -1 squared is 1, plus 4 is 5, but then you subtract 1, so you end up there with natural log of 4, right? Instead of natural log of 5. Okay, so that's a mistake. But I think the harder part here on these questions is determining what is the domain, right? Because the domain is a region in the XY plane, correct? Okay. And so you can look at the review and watch my explanation there of how to find the domain. To make a long story short, remember, when you're computing natural log, the domain of a natural log is restricted. You can only compute natural log of positive numbers, so not negative and not 0. So you have to make sure that this expression inside the natural log, x squared plus y squared minus 1, you have to make sure that is not negative, right, or 0. So what you're going to do is exclude points in the xy plane where x squared plus y squared minus 1 is less than or equal to 0. Those are the things that you want to throw out of your domain, right? Because then you'd be computing natural log of 0 or a negative number. So if you solve this inequality, what that means is you're going to throw out points that are inside this circle, or either on or inside this circle. X squared plus y squared equals 1. That's just the unit circle, okay? So that's just the circle centered at the origin with radius 1. That's called the unit circle. And so we have to throw out points inside the unit circle, because when you plug those coordinates into this expression, you'll get 0 or a negative number. So your domain ends up being this shaded region here. That's things outside of that's points outside of the unit circle. Okay. So if you look at the review tape again, it maybe will explain that the solution here a little bit better than what I just did. The other one I missed here was that I know of is down in problem 6. And again, I just made an arithmetic mistake. So when I was finding, let's see, the slope of this surface. So what was that surface? It's this surface. No, this surface, e to the x minus 2y. Okay. So when I was finding the slope of that surface in the direction of the vector u, which is given, well, here's the vector u, okay? So I was trying to find the slope of this surface, x minus 2y, in this direction, starting from this point, okay? Starting from this point. So, so I went through the steps, but one part of that is evaluating one part of this process of finding the slope is evaluating the partial derivative with respect to y at x equal 2 and y equal 1, because that's the given point, right? You also have to do that for x as well, but I made the mistake here on computing the partial derivative with respect to y. And I don't know what I ended up. Oh, I reversed the 1 and the 2 in the formula. So when I was writing the original solution originally, so this value turns out to be just minus 2, and then you plug that into your directional derivative formula, and you end up with 11/5. Okay, so my original answer there was a very complicated quantity, all right, but the actual answer is much simpler. It's just 11. All right, so so you guys can, so this is on the tape, and I have it correct on the tape. You'll see me hesitate a little bit when I make the tape, where I realize the mistake. Okay, but anyway, all right, so those are the only mistakes that I'm aware of, but there could be others. All right. So anyway, the answers here are posted. All right. On the Blackboard page, along with that tape. So I think you got plenty of stuff to, in addition to finishing your homework, right? You got plenty of stuff you can prepare for the test on Wednesday. Okay. So enough of that. Do y'all have questions that y'all want to ask? Certainly. Yeah. We'll provide those. So you can try to as much as you can. I really don't think you need one. So for the test, he's asking about the catalog of quadratic surfaces, right? So I really don't think that's necessary for the. Don't think that's necessary for the test. So just whatever you can put on your index card. That would be hard to get on the index card, but
it's going to be the same size.
Yeah. If you so you can keep your previous one and add to it unless you filled it all up. But if you want an index card, are damaged on an index card. Got some, so. Okay. Okay. Sorry, can I get one more? Yeah. All right. Well, let's go back then to talk about extrema, and we've got several examples here that that kind of illustrate some of abnormal situations with extrema. So, no, I don't think that these are typical extrema type problems, but just trying to illustrate some of the complications that arrive when you're looking for extrema. Let's see, that's the wrong note. So so recall from last time what we're going to use here initially to help us for those extrema, right, is look what are known as critical, right? And critical points, the definition for critical points slightly up there in the notes, but remember, critical point is where either both of the partial derivatives are zero. Okay, so the derivative, partial derivative with respect to x, or the partial derivative with respect to y, where those are both zero, or where one of those partial derivatives is not defined. Okay, and so that's how you look for a critical point, and then you know that you have a relative extremum that is a local maximum, or it could be an absolute maximum, or a local minimum. It could be an absolute minimum at a critical point. All right. So, so if you can find the critical points, then you will know where your possible extrema are located. All right. But the tricky point is, unfortunately, not all critical points will yield local or relative extrema. Okay, so you can have some critical points that where you think you're going to have an extremum, a peak point or a valley point, but it turns out that's not the case. All right, so that's kind of illustrated in some of these examples. But that same situation occurs. That same situation occurs in Calculus 1 as well, right? Because this process of finding a relative extrema is very analogous, right, to the way you look for relative extrema in Calculus 1. You look for critical points, and sometimes those critical points in Calculus 1 do not result in a maxima or a minima. All right. The famous example of that in Calculus 1 that's always shown to students is this function, y equal x cubed, just the cubic parabola, what I call the cubic parabola, which is really not shaped like a parabola. Looks like this when you graph it. That's what the graph looks like. But when you look for critical points, well, the derivative, of course, is 3x squared, right? So that is going to be 0 when x is equal to 0, right? So it looks like you're going to have a local minimum or a local maximum at x equals 0 at the origin. But that turns out to not be the case. Okay. You do get a bend in the curve there, all right? But don't get a local minimum or a local maximum. That is an important point on the curve. That is a inflection point on the curve, right? Because the concavity is changing from concave down to concave up, but it's not a local minimum or a local maximum. Okay. Right. Well, the same sort of situation can occur with surfaces as well. Okay. So you can have critical points that turn out to not be relative extrema. All right. Well, I don't think that happened though in this first example. So this first example that we went through last time was very straightforward. And so we found the I think there was one critical point here. Yeah, we found the one critical point, and we managed to demonstrate to ourselves, though it took a lot of effort, right? We managed to convince ourselves that not only was that a critical point, but it actually turned out to be a local minimum. In fact, it turned out to be an absolute minimum. And if you graph this surface, you can see very easily that this point, -233, really is not only is it a local minimum, it's an absolute minimum because the surface looks like this, okay? And there's the point -2333, right? So you definitely have a valley point there, definitely have a local minimum, but in fact, that's an absolute minimum because this surface never gets below this point anywhere, right? Okay, at all. So the minimum Z output here is for the whole surface is 3. All right. So that's kind of that first example is kind of the standard problem for extrema. But now let's look at some kind of unusual situations, right, that can arise. So let's see if we can find the relative extrema for this. See if we can find the relative extrema for this function. Now you can tell this one's kind of been rigged, right? So because of the nature of that formula. 1 minus the cube root of x squared plus y squared. That's kind of an usual formula, right? So it's like the author here has made that up exactly as an example you and we'll see what it's an example of. So first, let's try to find the critical point first before you worry about if the critical point really does result in a maximum or a minimum. And so to do that, right, you're going to find the partial derivatives, right? So let's see, what's the partial derivative here with respect to what's the partial derivative here with respect to x? Well, let's see if we can differentiate that formula with respect to x, right? So if you differentiate, I think to differentiate, right, you need to rewrite this cube root, correct, in the right form. So let's write that as 1 minus x squared plus y squared to the 1/3 power rather than cube root. Because to differentiate, right, we want to apply the power rule, correct, to find this derivative. So let's see, when we're differentiating, well, the derivative of the 1 is 0, right? So we can get rid of that. And now to differentiate this second term, well, of course, you're going to bring down the exponent, right? So you get -1/3. And then let's see, what else do we get here? X squared plus y squared that would be -2/3, right? -2/3, right? You subtract 1 from that exponent 1/3, but you have to remember the chain rule, right? Because here we just don't have a simple variable raised to a power, right? We have this expression raised to this power. So I'm going to have to multiply in the derivative of this expression. Remember, we want the derivative with respect to x. So the derivative of this expression inside the parentheses with respect to x is just 2x. Is that right? Yeah, okay. Because y squared, we're thinking of that as a constant. So when we take its derivative, we just get 0. So let's see, how does this, let's clean this up a little bit. So what's this really look like? Let's say, I think it's something like -2x, right, over, and then we're going to have 3, right, in the denominator from this 1/3. And then let's interpret this exponent properly. This is why I wrote the fraction, because x squared plus y squared to the -2/3, you invert that, right, to get rid of the negative exponent. So it would be 1 over x squared plus y squared to the 2/3 power. But let's write that 2/3 power now back as a radical. So 2/3 power means cube root, correct? The 3 tells us we're going to have a cube root. And what happens to the 2? See, the 3 here becomes the index of this radical, but what happens to the 2 in that fraction? Yeah, it stays as an exponent, right? Yeah, it's going to stay as an exponent. So you will have x squared plus y squared squared. Okay. All right, and remember, at some point, we're going to want to set this equal to 0, correct? Now let's find the, but before we do that, let's find the partial with respect to y, right? Because we need that set equal to 0 too. Well, this expression is symmetric in x and y, correct? So when we find this partial derivative, it's going to look like this partial derivative, except I think we're going to have a minus 2y in the numerator, right? Instead of the minus 2x. And then the denominator will end up being the same, right? So we have no work left to do, right, in finding that partial with respect to y, because it's going to look very similar to the partial derivative with respect to x, and we're going to set that equal to 0, okay? All right, now we have to solve these two equations simultaneously. When what values can you choose for x and y that will make both of these equations 0 simultaneously? Can y'all just see that by inspection? See, here you have a fraction equals 0. The only way a fraction equals 0 is if the numerator is equal to 0, right? So you know minus 2x would have to be equal to 0. But that means immediately what? X is equal to 0. Same thing here, right? If this fraction is equal to 0, that means the numerator has to be 0, right? So minus 2y has to be 0, but that means y has to be 0. Oh, so there's our simultaneous solution, right? Okay, there's our simultaneous solution there. So we're thinking we have a critical point at 0, 0. X equals 0 and y equals 0. Actually, now we could have figured that out also without bothering to solve these equations simultaneously. Robert, do you see why? I could have figured out right here before I even bothered to take the partial with respect to y. I could have figured out that 0, 0 is going to be a critical point. Do you know why that's the case? So if I just had the partial with respect to x, how could I have deduced immediately that 0, 0 is going to be a critical point? Because how do you get critical points? You get critical points when the two partials are 0. That's how we arrived at 0, 0 this way. But you also get a critical point when, but this is the one you mustn't forget. When no, there I said equal to 0. But when one of the partials is what? It doesn't exist, right? Yeah. When one of the partial derivatives doesn't exist. So you could see from looking at this formula that this partial derivative is not going to exist. Actually, this one either, but we could have noticed it immediately right here. This partial derivative is not going to exist when x is 0 and y is 0. Because what does that make the denominator here? 0, right? Okay. All right. That makes the denominator 0. Okay. So there's we could have immediately saying, oh yeah, okay, I must have a critical point at 0, 0. Okay, some kind of critical at 0, 0. Now I wonder if this is a minimum, or so I'm thinking, well, so I have a candidate critical point for two reasons. Okay, is this a maximum, or is this a minimum? By the way, 0, 0 is part of the domain of the original function. Okay, right? It's not in the domain of the partial derivatives, but it is in the domain of the original function. You can plug 0 in for x and 0 in for y in the original function, and you'll get 1, right? Okay, so this point is fine. It's in the domain, so it's part of the graph, right? It's not the graph doesn't exist at 0, 0. It does. Okay. So how do we deduce if that is a maximum or a minimum? Well, you have to, again, you have to kind of now use a little bit of logic, all right? So it's not automatic. Look at this formula, right? You have 1 minus this cube root, right? Of x squared plus y squared. But notice x squared plus y squared, that's always positive, right? That is, no matter what you choose for x and y, correct? X squared plus y squared is going to be positive. So you'll be taking the cube root of a positive number, and cube roots of positive numbers are going to come out to be what? Positive, right? Okay. So you're always subtracting a positive number, or I should say a non-negative number, from 1 in this formula. No matter what you choose for x and y, you're always subtracting a non-negative number from 1. Well, if you subtract a non-negative number from 1, you're always taking something away from 1, right? So you know this quantity then is always greater than or equal to what? I'm sorry. I'm sorry, I got it backwards there. You know this quantity is always less than or equal to what? 1, right? Okay. Because this number is always positive. So the largest this can be is 1, right? But is it ever exactly, is this expression ever exactly equal to 1? Is it ever exactly, is this expression ever exactly equal to 1? At the critical point, right? Okay. So you know this, your function formula is always less than or equal to 1 because you're always subtracting a positive number from 1 in this formula. And it's going to be exactly equal to 1 when x is 0 and y is 0, right? Because that means you would be taking 1 minus the cube root of 0, which is 0. Okay. So what does that mean about this critical point? What sort of so that is that is an extremum. What sort of extremum is that? Minimum? No, we said what? This quantity is always less than or equal, right? It's only equal to 1 at, okay? So it's always less than or equal to critical, right? So it's a maximum. So you have an actually an absolute maximum. It's not just a local maximum, it is a local maximum, but it's an absolute maximum for that surface. That surface can never be above 1, and it only hits 1 at critical point. Okay. Let's take a picture of this. I wonder what let's look at the graph of this. So let's look at a picture of this. And there's the picture. So where you get a surface that looks like this. Okay. So it's kind of a Hershey kiss there, right? Okay. Surface. There is our absolute maximum there at 0, 0. And you plug 0, 0, of course, in to mention, right? So the formula, it 1 as the output. So I should see it's 1. And notice it comes up to a sharp point, right? The surface comes up to a sharp point there. That's why partial derivatives don't exist here. Okay, they don't exist at this point. So you have a sharp on the short point. Notice you do not have a tangent. Not have a tangent at this sharp point. Remember how do tangent planes work? You're supposed to touch the surface, right, at the point, but not at the surface. So if you think of a tangent plane, horizontal tangent plane, you can draw one, right? But the problem is you can draw tangent planes lots of ways. Okay, so you can tilt the tangent plane, and it still just touch that point, right? And not cut through the surface. until the tangent limits would. It would still just hit that point and not cut surface. So you don't have a unique tangent. That's why you're lots of different like, it's sharp teeth. So just like for calculus 1, remember on have sharp valleys don't have right can so sharp valley. Oh, okay, so that was a little bit annoying, right? Because we found the critical point. It turned out to be an absolute maximum. That's great, but it's hard to demonstrate, right? Logically, that critical point turned out to be an absolute maximum. Right? You have to think about that inequality, right? Figure out that's an absolute maximum. So that requires some additional logic. That's a little bit, it makes us a little bit uncomfortable about finding extreme of right now. How hard is this really going to be to prove that critical point is an extreme value? Take a look at this one. Maybe that. So here we want to find critical points on this is a hyperbolic parabola. So it doesn't have a complicated formula, just y squared minus x squared. But the instructions here kind of give it away. It says show that this critical point is not a local extremum. And it's going to tell you how to do that by graphing the traces of this surface, in the xz plane and in the in the yz plane xz. Right? So well let's worry about what these traces look like in just a minute. But first, see if we can just find them. So we do have a critical point apparently, but it turns out to not be a local. All right, so what do we do? So what are the steps there? Yeah, you got to find partial derivatives, right? So this part is kind of automatic. Find partial derivatives. So let's find the partial derivative with respect to x. That's so easy. Isn't that minus 2x, right? And the partial derivative with respect to y, also easy. That's minus 2y. Ooh, so this looks like what we were looking at in the prior problem, right? So set these to 0 and solve those two simple equations. Minus 2x equals 0, minus 2y equals 0. Solve those two simple equations simultaneously. I think you know already what the simultaneous solution is going to be, right? What do x and y have to be? 0, right? So we have 0, 0 as a critical point again. Okay. So this means x has to be 0, right? This first equation, and the second equation means y has to be 0. So we have so the critical point's easy to recognize. Okay. It's 0, 0. But it turns out this is not a turns out you don't have a local minimum or a local maximum at 0, 0. And the suggestion for seeing this without graphing the entire surface, but I do have a graph of the entire surface, and then you'll see what's going on better. But the suggestion for seeing this without graphing the whole three-dimensional surface is graph these two-dimensional curves. So the trace in the XZ plane, right? So do you remember how to find the trace in the XZ plane? Remember the trace of this surface is not this surface, right? But remember the trace in the XZ plane means we're going to look at the XZ plane. So that's the plane defined by the x-axis and z-axis. So that's this vertical plane, right, that contains the x-axis and the z-axis. And that cuts through the surface, and where it cuts through the surface, that's just a curve, two-dimensional. So for this surface, not this one, y squared minus x squared, want to find what does the what does trace in the xz plane look like, and also what does the trace in the yz plane look like? The trace in the yz plane is cut through that plane, right, that contains the z-axis and the y-axis, right? And again, that will cut through the surface in two-dimensional. All right, so how do we find the traces starting with the yz plane? What do you do? How do you find the equation of that trace? This one. Remember how to do this? See, you're thinking you want the plane, the vertical plane that contains the y-axis and the z-axis, right? So that's going to be this vertical plane that contains the y-axis but goes straight up and down, right? So what's characteristic of that plane? What's the x value always in that plane? It's always going to be 0, right? So what you do is in this equation, you just set x to 0, right? Okay, you just set x to 0. So when you set x to 0, you do get a two-dimensional curve, right? You get a curve in two variables. You get z equal y squared. So we're going to graph z equal y squared in the yz plane. So here's the yz plane, and I'm trying to graph z equal y squared. Well, what sort of curve is that, obviously? That's a parabola, right? So you get a parabola like this. So apparently when you graph this surface, when we graph this surface in the yz plane, when we graph this surface in the yz plane, you get this parabola. So that suggests what? The surface is, so see, here's the critical point down here at 0, 0. So that suggests that critical point might be what sort of extremum? A minimum, right? Okay, because it looks like on both sides the surface is going up, right? Okay, on both sides the surface is going up. But now let's graph the trace in the xz plane. So in xz plane, you do what? You set y equals 0, right? So that gives you z equals minus x squared. So that's also a parabola, but what kind of parabola is that? Facing down, right? So you get a parabola like this. Actually, these two parabolas have the same shape. I didn't draw them very carefully, but you still get a parabola, right? So this parabola, this trace suggests that our critical point is what sort of extremum? A maximum, right? Yeah. Well, it can be a maximum and a minimum at the same time, right? So these traces are telling you we got problems, right? Okay. Yeah. So this critical point is not going to be an extremum, right? Cannot be an extremum. So what does the surface actually look like so that we can have these two traces? Well, what you get at the origin here is what's called a saddle point, all right? See, we're in 3 dimensions, so all sorts of strange things can happen. So you see, in what did we say? In yz plane, notice you get this parabola, right? But in the xz plane, notice the surface is going down. Okay, this is called a saddle, right? That's what that sort of. In one direction, it's kind of a minimum, right? But in the other direction, it actually turns out to be maximum. So it's neither, right? Neither. I have a local maximum. Have a nice critical. That's all it is, right? Doesn't stream that good. Stream. Oh, see again now. That took some extra logical deduction on our part, right? Not looking at the graph. If we'd seen the graph, then we'd figure not looking at the graph, that took some extra work on our part to graph that good point. Really did not correspond to a maximum or minimum. You know, that extra logic is that can sometimes be difficult. Okay, so that gives us not a good feeling about how to figure out critical points are actually local, absolute, absolute maximum. I'm trying to make you before we show you kind of a partial answer to this problem. Let's look at one more. Oh, maybe I don't need one more. No, I don't. Okay, so we're ready for our big surprise here. Okay. So that last example though does again provide really nice motivation, right? For this theorem, which is called the second partial test. So in this theorem, we're going to use the second partial to help us understand if we have a maximal. And nice thing about the test is, it's kind of automatic. Okay, so just involves calculus and calculations. It doesn't involve any sort of special logic that you have to apply to the situation. Okay, so but the theorem is a little bit complicated. All right, so that's the bad part. All right, so here's what you do. All right. The second partial test does have some conditions on it. It says the second partial derivatives have to continue. Second continuous, right? Okay. And it has to be the case that the first partial derivatives both are zero, right? So first partial derivatives have to be zero to apply this test. All right, so here's what we do. Okay. All right, so notice there's kind of there's a recipe, right? You have to calculate the second partial. And we're going to plug them into this formula, and we're going to keep the value that is always referred to as D. I don't know, right? Okay, so calculate a value that's always referred to. And notice the way D is computed, right? Take the product of the second partial derivatives, remember those things are supposed to be continuous, right? Okay, and which they normally. And then you subtract off the mixed second partial derivative squared, right? So take the partial with respect to x twice times the partial with respect to y twice minus the partial with respect to x then y squared. That gives you a value called D, and then we apply these tests using value. By the way, remember the mixed partial derivative. This says x first, y second, but you can do y first and x second. Because remember, those are the same. It turned out. All right, so what does this test now tell us? Look, it says if D is greater than 0, so if this number turns out to be positive and the second partial derivative with respect to x is positive, then though you have a minimum, not a maximum, but so you have a relative minimum, actually critical. So positive D, positive second partial derivative means relative minimum. Oh, by the way, you could use y. Now, if D is positive, but the second partial derivative is negative, right? So notice the signs are different. D positive, this one negative. Then that means you have a maximum. That's the maximum. Now, D, of course, can turn out to be negative itself, right? When you do this calculation, if D is negative, then that means you have a saddle point, right? So if D turns out to be negative, you've got a saddle. Don't care about the sign of the second partial derivative. D is negative and have saddle. Now, unfortunately, the test is not foolproof, right? As a fact. If D turns out to be exactly 0, which can happen, then that means, unfortunately, the test fails. Okay, and so you're sort of back to the bottom. Don't know if you'll have to discover. So, that's kind of a bad situation. But fortunately, right, that's only one value for D that messes things up. If D is positive or if D is negative, then you're going to end up with. So let's check this. I'm not even sure this is true, right? So let's check this for that prior saddle. See if the D value turned out to be negative, right? Because that in that prior example we had a saddle point. So let's go back and see what happens. Maybe it'll turn out to be boring, but let's see what happens in this prior example. So let's see, what do we need? We need the second partial derivatives, right? And then we need the mixed second partial derivative. So I need to calculate f(x)(x), the second partial derivative x twice, right? So that's so easy. What's that going to be? -2, right? And what is fyy going to be? Also -2? Oh, did I do it wrong? Is it just 2? Oh, this one is minus. Oh, yeah, I was getting overly optimistic, right? So this is +2. So that doesn't change the prior example, but oh, it may have screwed things up here. All right, maybe not. All right, so -2 for the partial derivative. There's a second partial derivative with respect to x, +2 for the second partial derivative with respect to y. What about now the mixed partial derivative? So x first and then y second. Is that 0? Because partial derivative with respect to x gives you -2x. But now when you differentiate this with respect to y, this is all just a constant, right? Because y doesn't show up there. So you get 0 here. All right, and now, so what's our value for this example? What's the value for D? Remember, it's f(x)(x)(y), right? Times f(y)(y)(xy), minus, and then f(x)(y) squared. So is that going to give us what we want there? Let's see, this is -2, right? And this is +2. And minus, well, that's just 0, right? Squared. So I get -4, which is, less than 0. So I do get a negative value for D. And so the theorem works there, right? Because negative value for D says have a sum. So that was much better than trying to make the graph and look at the graphs, right? Or make those traces. See how fast that. So see that we have a sum. But remember now, this test applies when you find the critical point by setting the first partial derivative to 0. If the first partial derivative is under 5, that's how you found the critical point. Where the first partial derivative, then this is not going to. Conditions of the theorem says the first partial derivative both happen, and also the second partials have to be. So sometimes that. All right. Well, let's try another example of that and see what we can figure out. Wow, this one looks terrible. Okay. So I think I do have a graph of this one, but I don't want to reveal that one to you yet. All right. Okay. Can y'all find for me the first and second partial derivative? So and remember, including the mixed second partial derivative f sub xy. That's good warm up for your test. Okay. That should be an easy problem. That should be an easy problem. Text, right? So you see what I'm asking you for. So f sub x of xy. You got to go through the whole catalog here. F sub y of xy. F sub xx. F sub yy. And then also f xy. All five of those. Remember, fyx and fy will turn out the same. So that's why I calculate 6. Like partial, or when you're finding second partial derivatives, they're really only 5. That's right. Okay, let's start walking through some of these. Did y'all get all these written down? All right, so And then we'll continue with the test, right? So what's the partial with respect to x? Minus 3 what? X squared plus 4y, and that's it? Yeah, because these two terms with respect to x are constant, right? All right, so that's nice. What about with respect to y? 4x minus 4y? Just the derivative of this term, right? Minus 4y, and then the derivative of that term, of course, is 0, right? So you get 4x minus 4y. Okay, what about with respect to x twice? Is that just minus 6x? And with respect to y twice is minus 4? Just the constant minus 4, right? Because the derivative of that is 0 with respect to x, right? So minus 4. And what about x then y? What happens there? So there's x first, and then what is it, just 4? Because that term with respect to y is constant, right? So you just get positive 4. Oh, right. Okay, so that's kind of the automatic part. And then conducting the test is also kind of easy, right? The hard part here is as it frequently is solving equations, right? Because you got to set the first partial derivatives to 0, and then you have to see if you can find the simultaneous solution to these two equations, and that's not always easy, okay? So finding simultaneous solutions to equations is not easy. And even if they're linear equations, this is not even linear. These are not even linear equations, because in this equation you have x squared. Linear equation would mean all of your variables are raised to the first power. So there's a whole course in finding simultaneous solutions to systems of linear equations. That's called linear algebra. All right. Okay. So this is not a trivial topic. But here, if you look at it just right, you can do it. Because look at that second equation, 4x minus 4y equals 0. I think that tells me that if you rearrange terms, that tells me 4y is equal to 4x, right? If you shift this to the right-hand side, now you can put 4x in here where you see 4y. So we get a break. So we end up with this equation, minus 3x squared, plus 4x is equal to 0. And I think I can solve that one by factoring, right? Factor out an x. And so you get x times minus 3x plus 4 is equal to 0. And that means one of these two factors has to be 0. So x is 0, or minus 3x plus 4 is equal to 0. And can we solve that in our heads? I think that means what? X is equal to 4/3? Because if you plug 4/3 in here for x, the 3's would cancel and you would have minus 4 plus 4 is 0. Oh, so there are the two values for x. And then what are the two matching? So what are the two matching values for y? So we have critical point. We have two critical points here, right? Critical points at well, if x is 0, see, notice this tells us y has got to be 0 too, right? So you have a critical point at 0, 0. And then what's the other one? Plug in x equal 4/3. Is that right? So that turns out to be what? 16/3? If I'm looking at that right. Okay. Did I solve this one properly? Yeah, I think I did, right? So yeah, so 4/3 and 16/3. There's our other critical. All right, so now we get to now we get to test these, right? Okay, so we want to know, are these are these a local maximum or a local minimum, or maybe neither, right? Okay. Maybe it's a saddle point, or maybe the test will fail, right? So that's where we're gonna compute now those values for D, right? So let's start with 0, 0. Let's calculate our value for D here, right? So how do we do that? It's going to be what? F sub XX at what? This point? 0, 0, right? Times F sub YY, right? At 0, 0 minus F sub XY, right? At 0, 0. So what do we get out of that? What's this going to be? Is that going to be 0? When you plug 0 in for x and 0 in for y, well, you're just plugging 0 in for x, right? Into the second partial derivative. So you have 0 there, right? Times a minus 4, because they're here, you're not plugging anything in, right? Minus, right? Okay, and then f sub xy squared, which is 4. Did we do f sub xy right there? There's f sub x, and then yeah, I think that's 4. So does this turn out to be, what is that, minus 16? Which is less than 0, so what does that mean? Saddle point, right? Okay, so this critical point, right, is a saddle point. Ooh, I'm very suspicious of that. So let's look at the graph right away and see if we think we did that right. So here's the crazy graph of there's the crazy graph of that function. So notice you get a really nice, pretty graph there. That surface, and right there is 0, 0. And notice that is a saddle point, right? But notice in this direction, it's okay. It's like a peak, right? But in this direction, on that surface at 0, 0, it's like a valley. So you have a saddle point. Maximum. So what about that other one? This must be 4/3, and this must be 4/3 and 16. It does not look like 16/3. So I do the arithmetic right there, but what did I do wrong? Oh, did I solve for the wrong? Did I solve for the wrong variable there? Or did I just do the arithmetic wrong? So did we don't agree that is x 4/3? Oh, x is 4/3, but so is y, right? Okay, yeah, all right. Because 4 times x equal 4 times y means x is equal to y, right? Okay, all right, duh. All right, so thank you guys. All right, so 4/3 and 4/3. I wonder if that would have messed our test up. Don't think so, but I don't know. All right, so wow, let's see if we can get through these. Let's see if we can get through these calculations now for. Let's see if we can get through these calculations now for D. So you've got to calculate f sub xx of 4/3, 4/3. That's the hardest one, right? And then f sub yy of 4/3, 4/3. Well, that's nothing because that's a constant, right? And then minus f sub xy of 4/3, 4/3. But that also is easy because f sub xy also, don't forget we're supposed to square this. So but f sub xy also is a constant, right? Okay, so these two values are easy. This is the one that requires a right, but not much. Actually, not much at all, right? Just that -6 times just -6 times 4/3, right? So we get here -6 times 4/3 is what's that, 8 or something, or -8? -8 times f sub y of 4/3 is -4, right? Minus then what, 4 squared? Positive 4 squared. So this looks like 32 minus 16, which is bigger than 0. Okay, so we're going to get a maximum or a minimum, but the question is, which one is it, right? So what does the test say? So our d value is positive, right? And now we're looking for that second partial derivative with respect to x, right? That second partial derivative with respect to x, was that -8 right there when we calculated it? So we're in the second situation, right? D is positive, and the second partial derivative with respect to x was -8, and that is negative. So we have a relative maximum at 4/3. Oh, nice. Okay. Which I think corresponds right there to our picture, right? So you can see we have a relative maximum. Okay. All right, let's take a break here, and then we'll finish with one last example. I think this example is frustrating because nothing works right in this example, but we'll come back and look. It's a simple formula, x squared, y squared. Find this one. And, I think the test doesn't go right. It's a problem. Okay. But we'll come back and look at this in a few minutes. So let's come back in 5 or 6 minutes and try this example. I don't think that second partial derivatives test is going to get us very far in this example. Let's see. All right, so here we have this, again, simple formula for a surface, x squared times y squared. So that is not a quadratic surface, though, even though you have x squared and y squared, because these two powers are multiplied together, right? So this is really a 4th degree term. So this is a quartic surface, not a quadratic surface. So this is not going to appear in our catalog of quadratic surfaces, right? I'm not sure what this, well, we've got a picture of it, so we'll see what this surface looks like in just a second. But we're looking for the relative extremum again, right? So so we just go through the usual steps, right? So we've got to find all of those partial derivatives, and while we're at it, let's go ahead and write down the second partial derivatives in case we find some critical points. We can apply the second partial derivatives test, right, to try to figure out what sort of critical points those are, right? So let's see, what is our partial derivative with respect to x? So that should be pretty easy, right? That's just going to be 2x times y squared, right? Because you'll apply the power rule to the x squared here, but the y squared stays as a constant. So you just get 2xy squared, and ultimately, right, we're going to set that to 0, but we'll come back to that in just a moment. And then the partial with respect to y, right, is kind of the same thing, right? You're going to have 2x squared y, right? And also we'll set that equal to 0, okay? So now we're looking at this system of equations, right? That we want to solve simultaneously. That's pretty easy to solve by inspection, though. It's pretty right that you're going to get solutions to this first equation, that either x is 0 or y is, right? Because you've taken a product involving zeros, correct? So either x can be 0 or y can be 0. And then same thing happens in the second, right? Okay, your x is 0 or y is 0. So you do have the same solutions. You do have the same solutions to both equations. But notice it's not x equals 0 and y equals 0, right? It's either x is 0 or y is 0. So your critical points, gonna have a lot of critical points here. Not just 0, 0, but a lot more. Critical points are of, how shall I write this, okay? Are of the form where x is 0, but the y can be anything, okay? The y can be anything. All right, so all points that look like this, x equals 0, but y can be anything, those are all going to be critical points. So what is that? What is that set of points? Where x is 0, but the y can be anything. In the xy plane, what is that set of points? No, in the two-dimensional xy plane, what is this set of points? Huh? No, I'm talking about what part of the xy plane. It's the y-axis. That's the y-axis, right? Because x is fixed at 0, but y can be anything. So that's the whole y-axis. So the whole y-axis is going to be all critical points, all right? Okay, so this is the y-axis, and you're going to get the same thing for the x-axis. X can be anything, but if y is 0, then you get a critical point, right? So that's the x-axis. So there are lots of critical points. That makes us suspicious already about these critical points, I think. Okay. All right. Well, let's go ahead and do other parts of this second partial derivative test, though. So let's see. What's the second partial with respect to x? That's going to be what? Just 2y squared, is that right? Because you just have this constant now, 2 and y squared times x. So that's just 2y squared. And what's the second partial with respect to y? Is that same thing, right? Except 2x squared? And now what about the mixed partial derivative? Is it 4xy? Yeah, right. When you take this, the partial with respect to x, and then differentiate that with respect to y, you're going to bring the 2 down, right? So indeed, you get 4x y here. So let's try calculating the d value for these type of critical point, right? Okay, that's points on the y-axis. So what would the, let's see if we can compute the d value here for these things. So we get what? F x, and then 0, but the y can be anything, right? Okay. And then f y, right? 0 y, right? The y can be anything, right? And then minus, and then what? F x y 0 y squared. But let's see what happens here. So here, when you plug y into this second partial with respect to x, well, you just get 2y squared, right? So you get 2y squared here times, but what does this one turn out to be? 0, because you're going to plug zero in for x in this formula, so you get 0. Minus, and then what does the second partial turn out to be? Well, there's the, I'm sorry, what's the mixed partial derivative turn out to be? Well, you're just plugging y in for y, so that's irrelevant, but you're plugging 0 in for x. So this turns out to be 0, right? Squared. So altogether you get what? Whoops, 0. Okay. That's bad news, right? That means that for critical points of this form, the test is going to fail, right? And I think the symmetric thing happens here for critical points of this form. You can test that, okay? But if you try computing the d-value for critical points of this form, you're also going to get 0, okay? So so the d turns out to be 0 again. So the test is completely useless on this particular surface. We have lots of critical values, whole axes of two whole axes of critical values, but we don't know if those are local maximum or local minimum or saddle points from the second derivative test. If you look at the graph, you can see what's happening though. There, well, I think you can see what's happening. There is that graph. So it's like we're getting, sure, I think along the y-axis, looks like we're getting just a trough there, right? Some sort of trough there in the surface. So it looks like these are really are absolute minimums, okay, on the y-axis. And same thing happens on the x-axis. I think it can't see it as well, but I think you have kind of this valley of the surface that's running it's running x-axis. So x-axis also absolute minimum. So you get lots of absolute test. Actually, you can kind of see it from the formula. You can kind of tell it from the formula if we had thought more carefully about the formula to start with. So you notice the formula is x squared y squared. So squaring numbers, right, you're going to come out to be 0 or positive. So that function can never give you anything that's negative, but it can give you 0 if x is 0. So the minimum, that function is 0. Going to happen exactly along the x-axis. So if we thought a little carefully, probably figured out, oh yeah, the absolute minimum here has got to be 0, and it's going to happen on the x-axis or the y-axis, just like we see in the picture.
Now, since it's that, why is it not valid to choose wish on script?
No, the test will still come out as 0. I did choose any point, David. This is any point, 0 y is any. But for any point, yes. So that means that from the test you don't know, okay? But then by on our arithmetic logic, right, and figure out what it's actually minimum. Yeah, absolute minimum all the way along the y-axis and also all. All right, so I've got a couple more examples, a couple more extreme examples. I want to show you one that's a little bit more, slightly more even complex than these examples. That's looking at this surface, which has a very simple formula, sine of xy, but it gives you a nice surface here. So again, we want to find, where are the maxima and the minima on this surface. So, but we'll look at that next time. And then I want to show you an applied problem, a word problem for, this is going to be an absolute maximum. It's a geometric word problem. But since we've done so many extreme examples today, let's save those for after the test, because we got to review that. We'll have to review this after the test, right? Anyway, because yeah, we'll have forgotten about it by then. So I'm going to introduce another topic now. We are through doing differentiation, at least momentarily, and now we're going to switch to integration. We had to get there eventually, right? Okay. So because it's calculus class, and that's the second important topic in calculus, right? Is integration. So we're going to talk about integrating functions of two variables now. We're going to start by computing definite integrals for functions of two variables. And the way we're going to carry out the integration is going to be very similar to the way we did differentiation for a function of two variables. We're going to integrate by holding one of the variables constant and integrating with respect to the other variable. So we're just going to do kind of the inverse of partial differentiation, right? Okay, but we don't call this partial integration for some reason. All right, but that's how we're going to carry out our integration. Let's look at a very simple example here. And I'm not going to explain what the meaning of this definite integral is, what it tells you, what its value is. It's just an example of a definite integral. All right, that's it. And how do we carry out this definite integration process, right? So notice you do have a function of two variables here, right? X and Y, and going to integrate. But now notice that we're going to hold one of the variables constant, and we're going to integrate with respect to just one of the variables, right? So the differential here tells you which variable integrating with respect to. In this case, we're integrating with respect to y, right? So in this integral, integrating with respect to y, and x, just thinking of that as a constant. That's just a number to us, right? Okay, so it kind of plays no role at all in the integration process. Okay, and it kind of just gets carried along. Let's see if we can do this. So this is a very simple integral. So we should be able to do this, right? So how do we do this? This is a definite integral. So first I have to find the antiderivative, right? The antiderivative of 2xy plus 3y squared, but I'm thinking of y as being the variable. So let's find the antiderivative of the two terms separately, correct? It's one of the nice things about integration, right? We can integrate separate terms separately, right? So what's the antiderivative of 2xy? Well, we're going to use the anti-power rule, right? So we will add 1 to the exponent of y, right? And divide by that new exponent, right? That's the anti-power rule, the opposite of the power rule for differentiation, correct? And the x is just there, all right? So it doesn't contribute at all to the integral. And then plus, right? Okay. Same thing for this term, right? We're going to integrate that with respect to y. That's so easy, right? You're going to use the anti-power rule again, so you'll get 3y cubed over 3. See, the 3 just goes along for the ride. It's just a constant. X is just a constant. That's why it's just staying in there, right? So there is the antiderivative. Remember, you don't have to add on the arbitrary constant c because we're doing definite integration, right? This is definite integration. But what do we do with our limits of integration? Well, remember, we have to evaluate our antiderivative, right, at those limits of integration, correct? And then we have to subtract, right? Okay, so let's see, what will we... So this is all arithmetic, right? What are we going to get? I'm going to first put in the 4, right? The 2 I could have canceled, right? So don't need those. So I get what? X times 4 squared? Plus, of course, here the 3's divide out also. So you just get what? 4 cubed, right? Minus, and then what happens when we plug 1 in there? I just get what? X times 1 squared, right? Plus 1 cubed. So all very nice there. Except the numbers are kind of big, right? So this is 16x. Well, not really big, but 4 cubed is kind of big. What's 4 cubed? 64. right? And then minus, what's this? X plus 1. So what does all that reduce to there? 15x plus 63. Is that right? Does that seem right? Did y'all notice some mistake that I made there? So notice that your definite integral has the variable x in it, right? But we're thinking of x as just being a constant. So that definite integral is a constant as far as we are sort of concerned, immediately, right? And of course, when you do definite integration, you expect your answers to be constants, all right? This is not an indefinite integral where your answer is going to be a function, right? Okay, this is a definite integral where your answer is going to be a constant. I didn't make an integration mistake there, did I? Did I make an arithmetic mistake? All right, nobody saw it? Okay, so it must be right. I'm going to let you guys try one. Oh, this is kind of the same one, right? Um, but we're going to let our limits of integration here be slightly different, okay? Because remember, x is a constant, so we're thinking of x as being a constant here, right? So you can use x as one of your limits of integration, because that's just like a number, okay? So as a limit of integration, x. You couldn't use y here as a limit of integration. That's the variable, right, in the integral. But x is just a constant, so we use it as a right. So try this one. X, is that the same antiderivative as before? I think it is, right? Isn't it? Or is it? Oh yeah, that's the same function here, right? So there's the antiderivative. So all you have to do is all you have to do here is change the limits of integration. Instead of 1 to 4, it's going to be 1 to x, right? So you can sort of start right here, right? Except this 4 now will become an x. So that should be easy. Okay, so I'm not trying to rush y'all, but I'm going to rush you, um, so that we can say the last thing I want to say about this. All right, so as I mentioned, right, all we have to do here is, since we already know what the antiderivative is, right, for 2xy plus 3y squared with respect to y, all we have to do is change our limit of integration, our top limit of integration here, right, from 4 to x. So let's see what happens when we do that. So you're going to plug x in, not for this x, right, but for the y, correct? Because that's the variable. So what does that give you? X cubed, right? So you get x cubed plus, and then what does this become? X cubed again, right? And then minus, and then of course what we get when we plug 1 in there, right? Okay, which we'd already done, which we'd already done there a moment ago, right? So that's 2x times 1 squared plus 1 cubed. Oh, the 2's canceled out. Yeah. Okay. So x times 1 squared right there plus 1 cubed. So now just do the algebra, right? Just gather like terms. So we have 2x cubed, right? And then minus, this is going to be x, right? And minus a 1. So it's something like this, okay? Remember, this is a definite interval. Now, look, what's important here though, is that when we're integrating functions of two variables, ultimately we want to integrate out, so to speak, both variables. We want to integrate with respect to both variables. So look, here we have integrated with respect to y. Notice that gave us an expression involving what? X. Now we can in turn integrate with respect to x. Okay, so we can integrate twice, first with respect to y and then with respect to x. By the way, we could have done it backwards, first with respect to x and then with respect to y, but I just happen to do y first because this a definite integral is a function of x. So here's the way you indicate that. Here's the way you would indicate this on paper. Okay. Right? So first, right, I'm going to integrate respect to y, right? Here's the limits of integration that I chose. These were just arbitrary. Okay. And then when you do that, inside, so to speak, definite integral, right? You get this, correct? You get 2x cubed minus x minus 1, right? Isn't that what we got? But now you can integrate this again, except now with respect to x. And you can integrate out, quote unquote, the variable x. You integrate out the variable x, then you're just going to end up with a constant as your result here. Okay. Let's see. And these limits of integration I just made up. This is called an iterated integral. That's what the book calls it, but more commonly called a double integral, right? A double integral. Notice first integrating with respect to one of the variables, and then integrating with respect to the second variable. Let's see. So what is this? Just to finish off here quickly, what does this double integral end up as? So what is the antiderivative here? 2x to the fourth over 4, right? Minus x squared over 2, is that right? Minus, be careful here, what? X, and our limits of integration, right, are from now 1 to 2, okay? So now we just have to plug in those values. Let's see, that's 2 times 2 to the fourth power over 4 minus 2 squared over 2 minus 2, right? Minus, and then let's see, 2 times 1 to the fourth power over 4, right? Minus 1 squared over 2 minus a, I think I can do that. Think I can do that arithmetic? I think so. Okay. All right. So that looks very much like now, like just like a calculus 1 definite integral problem, right? Okay. If I filled in the values right. Okay. All right. So that's the process that sort of we're going to repeat many times now here. Okay. We're going to integrate with respect to one variable and then with respect to the second in one of these so-called double integrals. Now, what I haven't explained to you at all is what problem have I solved with the double integral? So what does that double integral represent, right? Okay, what's the meaning of that, right? what have I done? Okay, by shooting that double. So I have to attack some physical meaning, right? Okay, probably some geometric meaning to that double integral. So, so that's the real hard part, is not carrying out sometimes double integration. Now, usually the hard part is not carrying out the double integration. That's all kind of automatic, all right? But hard part is figuring out what those double integrals mean, right? And when we want to use a double integral. Okay. All right. So well, we're going to take that, of course, up at length, right? Okay. In the coming sections. All right. So we're done, right? We've run out of time. So already I'm completely out of time. I forgot the roll, so y'all gonna have to sign the roll. So try to sign the roll, sorry about that. And the test is Wednesday, right? Okay. So study well for the test on Wednesday.